Okay, so today we'll start with a very important concept on what is known as spatio-temporal modeling, or this is basically where you make use of some sort of understanding from your sequence modeling or RNNs in order to extend understanding of spatial features. Now, this is of relevance for activities where you want to do analysis with videos, and there is something over there as well. So let's get into that, and then you will get into it one by one. And the primary part over here is to understand spatio-temporal. So spatiotemporal has both of these parts, that there is a spatial component and there is a temporal component. So you need to take care of both of these aspects as well. Now, how I would start is essentially I would go through a basic revision of concepts, and this would be in terms of trying to explain essentially that if we extend up one more dimension, which is till now you just had spatial dimension in x and y, but now that I'm extending one more dimension along with x and y, I'm also getting the time dimension or t. Then what is the challenge which is going to happen over there? Then from there we'll enter into the basic concept of a spatio-temporal deep learning, and from there get into a particular case study, and there will be the multiple case studies which I will do. In fact, like there are just two case studies which I'm doing over here. The first one is what is known as surgical tool classification. Then we'll get into the point of temporal deep learning without RNNs, and if there is a way of doing that. So that's also critical in order to understand that not every time whenever you have a temporal sequence that you would need a recurrent network in order to solve it. And so let's get into the basics. Now the point is that whatever you start with, the starting point is your input over there. And now in case of 2D CNNs, what we were doing is we had images, but now that we have a 3D CNN model over here, this is something which also has say videos to it, and that makes it really something which is very crucial for our understanding. So if you go into videos, so first and foremost, we need to understand exactly what is a video, and how will you really denote whatever demonstrates a video. So what is the data structure essentially, or what will be the tensor representation or the tensor size for a video. So now, typically say for an image, what you had is that you had this kind of a representation, and then you had your rows and columns. Say this was M cross N, and because you have colors over there, so there are three different channels for representing color, and that becomes, and again for my representation as a tensor over here, we will be representing that as a 3D tensor, and then the channel space is or the third dimension. For me over here, it's going to be the first dimension of the tensor, because that's how we typically prefer representing it in PyTorch. So here, this first dimension which I'm using, that is essentially the dimension of the channels. So red, green, blue, these colors are what will come down over there. Now that I have a 3 cross M cross N, now for any kind of a convolution which I run down, so the convolution also has a similar 3-channel structure for the convolution kernel, and then if I have that as W cross H in size, then once I convolve, I'm able to get down a set of outputs. Now the point is, what do I do when I have a video which can be represented something like this, that it will have M rows and N columns and T number of such timestamps. So a video can pretty much be assumed like a stack of lots of images itself. Okay. Now the point is that in general you would say that a stack of images is going to be just in a 3 dimension, but then you also need to remember that it's a color representation scheme over there. So what that would mean is that it's not a plane, but it's a thick slice over here, a slice which consists of multiple channels, and this slice is stacked one beside the other. So this is one slice, then I have the next slice, then next slice, and so on and so forth. It keeps on going. So essentially, that's where this tensor would end up becoming a 4D tensor. Now, for a 4D tensor of this kind of a type, one way we represent is time cross channel cross M cross N, or there can be another way in which you can represent it as channel cross time cross M cross N. Now, that is purely up to your understanding of how you would like to associate it. but the way in which this tensor is represented over here is a very standard logical way in which we generally represent these kind of image and video tensors, and we make use of them. Now, for understanding what happens over here, so the point is that you have this whole video. This video can now essentially also be sliced up in terms of its channels, and that's what I was telling. So this can be assumed pretty much as a group of red, then a group of green, and then a group of blue. Now, for some reason, the green did not appear properly over here. So this would essentially mean what I'm doing now is that I have basically single channel tensors over here, and I'm stacking them over time. So now doing this will be an alternate representation. Okay. Now, what would be your opinion about using the former versus using this one? So now that you have done a lot of classes, now if I ask you this very simple question, in what kind of a condition do you think that the previous one is helpful, and in what kind of a condition do you think this kind of representation or organization is useful? You can type in the chat or you can unmute. Okay, so if you're confused around it, so let me tell you. So now, in generally a CNN, what you would do is that your number of channels is associated with your size of the tensor. So now, whenever you are convolving, then the total number of channels in your tensor is equal to the total number of channels in your input, and the number of channels in your output tensor as a result of this convolution is equal to the total number of convolution kernels which you had taken over here. So this is predominantly what is very basic to any kind of a convolutional neural network. Now here also, that is the basic concept which we are going to make use of. So now, when I want to organize my data, if I organize it very specifically using these kind of concepts, then that is going to be of use. Now, in the previous case where I had the organization such that the first channel is time, and then I had 3 cross m cross n, or basically it's a time stacking over all images. In that kind of representation, I would be very easily able to look into a frame by frame kind of an analysis. Whereas over here that I am representing my video in terms of a channel cross time cross m cross n, I would be very easily able to handle a temporal variation in space for each of the channels. So now here this kind of a representation is something which is very topically relevant for a actual 3D CNN which is going to make use of videos. So let's get what that would be. So you would need a very specific structure of convolutional network in order to handle videos. So now for that, let us have this simplistic analogy. So whatever we saw in the earlier slide in terms of a stack of frames of red, green and blue, now I replace those stack of frames with these blocks. So red is basically, so the block in red which I see over here, this one is essentially the stack of all frames of the red channel. The one which I see in gray corresponds to the stack of all frames of the green channel, and the one I see in blue represents the stack of all frames from the blue channel. And now I am going to make use of all of this. So what I do is, then for convolving, I will need a convolution kernel. Now this convolution kernel essentially should also be a 3D structure, because I'm going to do a 3D convolution on top of it. Okay. Now say that the time dimension of the convolution kernel is the same as the time dimension of the input block. In that case, there is no uh, thing as such like a volume output which would be created, but then that would lead to just one single channel of it. However, if this time dimension over here for the convolution kernel is less than the time dimension over here, which is the time dimension for the block completely, in that case you are going to get a finite output. And now from your 2D case to 3D case, it's not so complicated to really extend. So whatever was the kind of an operation, atomic operation for one single spot which you were doing in your 2D, that whole thing now gets extended onto 3D. Now this can be imagined to be videos. This can also be imagined to be actually spatial 3D data. So something like what we do with medical images, like say magnetic resonance imaging or with computed tomography, where you actually have a full scape of 3D data available to you. Now there, if you wish to actually do a convolution, then your convolution kernel should also be working along the z-axis and not only along the x and y axis. So these are some critical points which you need to really keep in mind. So corresponding to one convolution kernel, I'm going to get one block output over there. Similarly, if I go to the next convolution kernel, I will be getting another block of an output. If I use another convolution kernel, I get another block of an output. I use another convolution kernel, I get another block. So now you can pretty much see this is again just a very simple extension of the 2D case of convolution to the 3D case, and not so complicated to understand. It's a very trivialized example, if I would like to say. So now the number of channels in your output is equal to the number of convolution kernels which you had over here. So that's also that relationship which it is obeying over. So now this can be one way of handling videos and how you can process videos with a CNN. Now once we know that this is how you would wish to process your videos within a CNN, the next point is, can we really estimate what is the compute complexity and what is the data complexity of running all of this convolution through this process. So now let's get into convolution on video tensors and what will happen as a result of that. So if I have this video which is represented like this, and I have my convolution kernel over here, and that produces one channel of an output. Great. So the size of this channel is now going to be something of this sort. So where the width of the channel, width of this output tensor, one single channel of that output tensor is equal to basically m minus w plus 2pw divided by sw, which is basically the number of strides or possible valid locations over which my convolution kernel can move on the original input tensor itself. Now it will be able to move along the x direction. It will be able to move along the y direction. Similarly, it will be able to move along the z direction. So I have three directions in which it can move. And now the output tensor size is going to be accordingly defined in all the three directions. Okay. So now what we need to do is, this is a very straightforward extension. In fact, you can solve it yourself and you will be able to find out the same as well. So the challenge which essentially comes now that you are able to understand what your convolution will work and how it will do. Now the challenge will come in terms of understanding what is the total number of learnable parameters and where your calculations are happening. And that's really something to be worried of at this point. So say for this example itself, my output is something which comes like this. So now if I take a very standard case that I have a video which has m equal to 224, which means that I am taking an isotropic cube. So I will take x direction, I will have 224 elements. In y direction, I will have 224 elements, which means that 224 rows, 224 columns. And on top of it, I will also be having 224 time slices of this whole thing. And then that's something which I'm going to make use of over here. So now what we will have is, in typical way, this OW is going to come out as 222. So now if you look into it, I give an input tensor of size 224. My output tensor over there will be 222 elements. So now in a typical case where say I have 16 channels, in that case my output is going to come to be of this size. So this is where my assumption is that I have 3 channels in my input. I have 100 temporal frames. My number of rows and number of columns is 224 cross 224. And now that I have 16 channels of convolution, which means that 16 convolution kernels, then my output is going to be of the size of 16 cross 98 cross 222 cross 222. And this is not anyways complicated. There is a very straightforward way in which you can find it out. So standing on top of this, if I go to the whole concept of spatio-temporal deep learning. Now there will be one thing which you can pretty much understand from this one is that there's going to be a lot of compute complexity and there is going to be a heavy space complexity requirement as well. So as a result of that, your total memory requirement is not going to be any more trivial or as simple and straightforward as it used to be when you were just trying to run a bunch of 2D CNNs. So now it's not just one single 2D CNN, but it's a full 3D CNN which is running in this form. And over there, the memory complexity is going to go high. So in the earlier case, you did see that because of increase of one single dimension over here, which is the time dimension, there was an increase, a couple of times of increase, or basically the number of frames you are going to take. It's going to be that many times that it will increase in terms of the size. So there need to be a way of tackling this, or essentially understanding how can there be an alternative to doing all of this. So if we get back to our video point over there, this essentially is going to be my whole model of the data. What I can do is, if I do something like this, then I take one single frame. I don't take the whole 3D data, but I take one single frame over here. And I pass it through a neural network and I get a bunch of features. Now, this will not be that complicated for you to understand at this point, given that we have already covered the concept of an autoencoder. So in case of generative models and stuff which we were doing with adversarial learning, we have already covered what is the concept of an autoencoder. And in an autoencoder, what you are going to essentially do is, it's an unsupervised learning mechanism in which you use a reduced space, or you learn somehow to produce a reduced sized latent space which is capable enough of predicting out what should be the ideal output over there, or whatever is the expected output. Now, if you are able to predict an output from that reduced dimensional latent space, then that is enough to predict out that it has the same amount of features, or it is conducive in terms of the number of features which are supposed to be present. Now, given that fact, if that is going to take place, then what I can have is, if I encode my video using an autoencoder on a frame by frame basis, then for every single frame, I would end up having a 1D representation over here of latent space, and say that there are k number of neurons which I use for doing that 1D representation. Now, for every single frame that I have it, so, and I have t number of frames over here, so I will get down that t cross k size representation over here. And this can be a much reduced form, low memory complexity way in which I will be able to tackle this problem. So where we get to use that? So one of these examples is a use case which I have from one of our earlier papers from CVPR 2017. Now here the idea was that what you see in this small video snippet over here is essentially a surgical video being performed. Now, a video of a surgical, some kind of a surgical process. Now, when I mean a surgical process, that essentially implies that there is a human being and there is something wrong within the body, and you will have to cut open the body and then basically employ some techniques in order to get that one working, or correct your problems which are present within the body. Okay, so now given that that is the very fundamental and basic understanding of what is a surgery, the next point where I will come down is that not all surgeries are where you need to cut open the body and in an open body you see it. So there is a group of surgeries which are called as endoscopic surgeries, where you basically have a small tool going through a small pipe which is inside your body. So it will be something like if I have to operate something over here, then something on my hand, say over here, then instead of cutting open this whole part and then operating something and then stitching it up completely, I'm going to make a small hole, then put a tube inside, and that tube is what is called as a laparoscope. Now, that laparoscope can carry multiple things inside. So this tube becomes a non-frictional thing. Once the tube enters, now within the tube you can put down a lot of tools and back and forth you can keep on doing. So here, if you see in this small video, that is what is essentially happening. So there is a tube, that's why you have that circular periphery over there in the video which you can see. And whatever you see over here, they are what are called as tools. And there is one which is something like a pinch kind of a tool, which is called as a grasper. Then there is a hook-like tool, which is pulling things apart, and that's essentially what is called as a hook. So it's trying to cut out a part of the organ, and this is where there is a gallbladder resection surgery going on. So the gallbladder in your body has to be removed out, but then they don't open your complete stomach and try to remove your gallbladder. And here they're essentially basically putting a small tube, and they would be cutting and chopping your gallbladder into small pieces and then put it in a pouch and bring it outside the body. And so essentially in your stomach you will just have a small hole which is smaller than the diameter of a pen. So it is not even this thick over here, which is the diameter of a pen. And it takes much faster to recover, because you go, your surgery happens, and next day they would put just a small plaster on top of it and you are released. And then in a very good condition, and if you are following the doctor's advice, then you would be recovering up pretty much within a week or so. And then recovery means you are anyways able to join your workforce and do your work and everything, other than some very laborious jobs kind of things which you cannot do. But anything where you sit and work from a comfort of not so much of physical movements, you can keep on doing that one. And it does not take longer to recover in a sense, like that hole which has been created, that has to be healed. So here what you see is that there is a surgery being performed. Now what is critical is these kind of surgeries are very costly, and they cost in terms of two different things. One is the operating theater where this surgery is performed, that has a standard maintenance cost, because this is a very clean and safe space to do that one. And these are very, very different kind of ones. Next is that there are a lot of instruments which are getting used, and typically these are also done with robotic assistance. So because it's a tube which is just of this size, and there is a tool which is going down. So obviously your finger, which will have this order of a movement, that cannot control this one. So there has to be some sort of an actuation mechanism. It's a shadow robotics concept which is used over here. So you keep on controlling over here, and there is a reduced actuator which goes inside over here. So if your movement of the finger is say by one say in the order of about 4 or 5 centimeters, then over there the actual device is going to move in the order of say 30 to 40. Say if you are moving 3 centimeters, there it is going to move 3 millimeters, or even lesser than that, say 0.3 millimeters, or 300 microns, as we say. Now, as a result, what this allows you to do is you have a much more precise control, and you don't have to worry. You keep on working with your hands in the same way as you are doing. So there is a company called as Intuitive Surgicals, and you can look it up on the web. So this company makes out these robots. Now, what is imperative over here is that because the surgery costs a lot of time, and when you enter a patient into a surgical room, you have to prepare a patient. It's not like you just have a cut on your hand and you go to BC Royal Hospital and then they start immediately dressing and doing it. But over there also, you know that typically if you got a cut on a hand and they are going to do a stitch, then it's going to take you 2 hours very easily. And there will be different processes in which first they will clean, then they will sterilize that area, and then sterilize all the devices, which is make them germ free, and then they would start the whole procedure, and then they put down the plast and everything, and then finally when all of this is over, the last phase comes down where they are going to write down the prescription on your medical record book, and that is much more trivial and much faster actually. So here that this is what has to be done. There are two important areas which have to be solved, and this sort of came to us as a problem statement from this particular company. So one is we need to understand what is the total time for which this every single tool has been used. So say you are seeing these two kind of tools over here, grasper and a hook. So for how long has the grasper and hook been used? This is the first thing which has to be answered. Now the next thing which has to be answered over here is that how long will the surgery last? So I am in a certain phase of a surgery. Say the surgery has started about a couple of minutes ago. Then how long will it last? So now this has two different problems. There is a classification problem. So which is the tool which is currently being used. So over the period of surgery, if you can count for how many seconds a particular tool was getting used, then you know the total time of use of this particular tool, and then that is going to indicate what is the total usage case for a certain kind of a tool. The next one which you need to understand is basically for how long will the surgery last, or what is the next upcoming phase of surgery which would be there. So that is something which is a prediction job which we are doing over here. So for that, here if in this kind of a thing you make use of it, so this typical videos are something like in the order of a couple of hours, and the point is that this kind of a model needs to run in real time. So initially we have for training purposes videos available, but on the product scale of it, this will just be a video feed which is coming from the instrument itself. And now if you really want to make use of that, then it's challenging. So what we did was something like this, that instead of treating this as a complete video tensor, you start extracting frames and you do a frame by frame analysis. Now on that frame by frame analysis, what was initially done is you crop it, normalize and everything on, so that you get it down into your standard format. And then we used a very standard CNN. So you can use a pre-trained CNN which takes care of RGB natural object images, something like a LeNet, not a LeNet, something like a GoogleNet or a ResNet, or any of those networks which were essentially designed and trained in order to solve the image net problem. So you can take any of these kind of networks over here which are already trained, and then you feed this video in terms of extracted frames to it. Now the whole network over here was trained in order to classify the object which it is seeing in this image. But then these videos were not used for training that whole network. So the network, say if I take a out of the box GoogleNet from the model zone, then this network is capable of essentially recognizing simple objects like cats, dogs, ball, car, ship kind of stuff. But then it is not trained in order to recognize these kind of surgical tools like hook or clipper or grasper. So that is going to create a bit of problem for me. So now that it is not able to recognize them, then what will it say? So what we do is that you don't get too much into that part of the understanding. So you can essentially remove the classification neurons over there in that network, and you have just the fully connected layer before the final classification layer. So if I'm looking at a VGG net, a VGG 16 or VGG 18, something of that sort, then uh, essentially I don't have this final classification layer. So what I'm left with is just that 4096 neurons before the final classification layer. Now from there, we add a new set of neurons, and they correspond to whatever classes of tools are present over there. So now, with whatever classes of tools are present over there and this new neuron added, I can take these frames, and then if these frames are labeled somehow, not for the location of the tool which is present over there, but it is grossly labeled for which is the tool which is present over there. Then I can train this neural network. Now that this neural network is trained on top of that one, so this can essentially recognize my tools which are present over there, or just give me a class label of what is the tool which is present in a different frame. Now from there starts the fun. So what we do is, once this training is done, then I remove this final layer which has the classification labels, and now I am left with only my features present over there. So I take in those features and I feed them as input to my LSTM model. So this LSTM model over here now is going to take all of those features as my input, and then this will take it over all the group of frames which come from. So for every single frame, I would have, I will essentially have one single type of a feature representation which is coming down. For the next frame, I will have another feature representation. For the next, I will have another. So now if I am given a set of 100 frames on which I want to do, then over 100 frames, I'm basically given down a 1D feature representation. Now this you can treat pretty much as one of your language vectors which goes into your input, either a language vector or a word vector model essentially. Okay, so it can be a word vector, or if you are trying to do something like character modeling, then these can be basically that one hot encoding kind of a thing which goes into your recurrent neural network over here for solving all of this part. So that's the fundamental assumption over here, that these features are representative enough, and that becomes my temporally varying sequence which goes as my input to the recurrent neural network. Now here we make use of a very special type of recurrent neural network called as a long short-term memory, but then there is no hard and fast restriction on what kind of a recurrent neural network you can make use over here. So you can choose your whichever you are comfortable with and whichever you wish to like. So whatever is your favorite RNN. So that can be an LSTM, that can be a gated recurrent unit. It can be any of these kind of recurrent neural networks which are of use. So now the point over here is that you put down this whole time series modeling into this one. Then from there you will be able to generate a set of classification outputs. And now this classification output can be a prediction which is generated either by giving this whole time series model into your LSTM model and essentially get down only one output, or this can be one where I'm trying to generate such that for every single input, and it depending on having seen whatever was before it, so all that series of inputs over there, it's able to produce one single kind of an output. So this can also be another way of doing this modeling. So this essentially comes over here to solve multiple number of purposes. So let's look at what we were able to produce. Now this illustration over here shows you basically the different kind of ways in which we are able to solve these two tasks. Now if you look over here on this video shows that a surgery has started and it's in a certain phase and there is some operations going on. So I will take it slow. I will let you guys take some time and observe this one itself. Yeah, I'll come to the whole training process and then the tuning process and everything. So just observe the phases of this surgical video, and then I'll come and tell you the whole story of how this training data and everything was obtained and how we started doing it. Because this is important in order to understand like what is happening over there. So let me come to the phase of this one. Now that you have seen this one, so how this one was obtained is there are multiple challenges. So the recent one which is going on today is what is called as the Endovis challenge. So there are so what you can do is that there is a website called as Grand Challenges in Biomedical Image Analysis, and there are also multiple of them which are called as endoscopy vision challenge. So if you go and search up for endoscopy vision challenge, and you will end up landing on the Grand Challenges in Biomedical Image Analysis page itself, and there you would see that across the years that these multiple companies on endoscope and for robotic surgery have been putting up videos which are classified and annotated. So how they annotate is that every single frame is annotated by an expert for what is the kind of a tool present. There have been more recent ones where they have started putting down what is the class of the tool, what is the location of that tool as well. So I don't have those granular details over here, but you can actually look up for the other papers which we had published around this one, and you will get to that. In fact, a good way of looking at would be the paper over here is cited, so you can go down over there and find out exactly from what source all of this was taken down. Now, during the training phase, this whole series is available to you. So you have a video, and you have the different labels given down, all the different classifications for it also given down along with. So what you are going to do over there is you take this on a frame by frame basis, and then when you are training this first CNN for your feature extraction, over here you are going to basically train this in order to classify what is the class of the tool which is present over there. And once that is done, you chop off that classification layer and you take only that feature layers over there. So in this paper, you would see that there are different ways in which we had done. There were different architectures. So there was VGNet, there was GoogleNet, there was ResNet, all of these which were taken down over there. And they were either trained from scratch or it was pre-trained image-net pre-trained CNN model which was taken down and then it was modified. So there are pros and cons of how their performance was varying. More or less they were along the same range, but there was just a 5% of a plus minus variation which used to come down over there. So here that this is the whole factor. What we were doing is once you train the CNN to do that, and then you push it onto the LSTM. Now from the LSTM, what it is supposed to do is it's supposed to predict out this upper part which you see. So this top part, you see that it has some blocks. It says P1, P2, P3 kind of a thing. So the one on red basically means um, which is the current phase. Now, phase of a surgery is you are doing a task. Say I'm trying to make coffee or I'm trying to make tea. Then there will be different phases in which I will be doing. The first is I will boil water. Next I will pull a cup. Next I will take a tea bag, put it in my cup. I will take the hot water, pour it in my cup, and then I pull out the tea bag. Then I add sugar, stir it, and if there is whitener or milk or anything, I add that and then stir it, and then I have it. So this each of these things is what is called as a phase in which it goes on. So similarly in a surgery also, it's something like you will cut open, next you will chop it off, you will put it in a bag, you will pull it out, then you will again go in, clean that area, drain out all the blood, then seal it, all of these kind of stuff which is there. So they are called as phases of surgery. So here the point was that you also need to predict the phase of a surgery which is coming. Now, phase of a surgery is not always a linear process. So sometimes what happens is that you cut, then you drain blood, then you put the organ in a bag and then you pull it out. Versus there would be another where you cut, put the organ in a bag, then you pull it out, then you drain the blood and then you seal it. So there can be two different ways of these things happening. Now in this video itself, you would see that there was a time when it was in P2, and from P2 it could show that it would go to P3 or it could go to P4 or P5, any of them. So if I just scroll it a bit back, so it would just come. So at this stage, so this is the stage where you see that it is on P3, but it has a probability of going to P6 or P7, and it shows out a probability of 0.71 and 0.29. So this is what was interesting over here, that it needs to come to this point where it's not just only telling by looking at a temporal sequence of frames what is the phase of a surgery. Now the point is that which is the tool which is present is an instantaneous fact that you can always tell very easily that this is currently what is present. But then what is going on now is not based only on an instantaneous looking at that image. So you will need to look at all the frames which have been there before that, how things have worked out on that, and based on that only you will be able to tell what was the activity which is going on till now. And then what will be the activity which comes after this is sort of an extrapolation or a prediction problem which is present over here. Now that prediction problem is not just a LSTM which does it. So along with the LSTM, we also had some sort of a graph model in order to predict it. So, but nonetheless, and then that graph model was something where the edge weights and everything was learned based on prior evidences. So what was and these are what are called as state transition probabilities, and this graph is also represented in terms of a matrix which is called as a state transition matrix. So that is another part of this thing, how it keeps on going on. Now here the point was that you would see that after a point of time it will be able to isolate itself and say no, actually a different phase is expected now, and it still hasn't come. So anything which is not in solid, anything which is solid and green is a phase which is over. The one in red is the phase which is happening now, and then it will transition onto with the probability of 1 to that next phase which is upcoming. Now where this helps out in the complete caregiving environment or during surgery is that with every single phase you have a set of tools which are associated. So these tools are very, very specific to this particular phase of surgery to go on, and that set of tools need to be prepared before your phase of the surgery is commencing. So now if you are able to predict out very accurately ahead of time that this is the next upcoming phase while I am at this one, then you can get prepared with the tools. So this is the same as like in you are traveling in a train, and then you have a list of stations and your current station it's showing, and then what is your upcoming next station and in how many minutes you are going to reach that. So if that keeps on showing up, then you are very you are sort of like prepared. You don't have to panic as a passenger in a train that that you will be missing out on your station or not. So you don't need to keep on looking outside the window and counting the stations, but there is a board which is showing that this is your upcoming station. So you just keep a focus on that upcoming station's display, and when it shows the one where you are supposed to get down your stop, then you just get down over there. So that's the whole part. So we have that kind of a, say, train movement strategy, or a metro movement kind of a display, which we created for surgical videos and for actual robotic surgery which is happening, and then the whole analysis is video based. So it does not make use of any other sensors in order to do that. Now, that is not the only way of doing. So essentially, in the earlier model which you saw is that there was a CNN which was getting used, and along with the CNN, you had coupled up a LSTM model, and then this CNN-LSTM model together helps you in solving this problem of looking at a particular video and then saying what is the tool being used currently, what is the phase of that activity, and then what is coming up. Now, this is another way where we were trying to analyze human activities, or this is from the kitchen videos or the kitchen activities video data set. And here the point was that you analyze these kitchen activity videos and then tell as to what is the next phase of thing which is going to come up, and what are you doing in this video, what is the activity which is being monitored over here, or is being viewed. So here the task was something like this, that there's somebody who is trying to make tea, and then what you are going to do is you extract a set of frames over there, and then you crop it down, and then you feed it to the CNN. But now from the CNN, we don't feed it anymore to an LSTM in order to do that modeling, but now it becomes more of like a moving window kind of an approach. So you have a neural network. What it is going to do is you stack these features on frame by frame basis. So if I am currently at my TH frame, I will stack the features from T-1 to T-4 along with my TH frame, and then this becomes a one single column vector. And then this whole column vector is fed as an input to a fully connected neural network, and then you keep on building the fully connected neural network to get your output over here. So that is the way in which this whole thing is done, where you are not making use of any kind of a recurrent neural network in any way. Now from there, you can also get this activity video done. Now there is a bit of issue with the linking of the videos. Now here what it was doing is that there was this whole activity of pouring water in order to make tea. So there would be a person who, you can see that electric kettle over there. He comes to, he picks up the electric kettle, fills it up with water, and then heats it up, and then pours the, takes a teacup, puts a tea bag, pours the hot water into it, removes it, and then and now over here in green, what you see is whatever was the ground truth activity level. So this was what the whole image frame was labeled for, and in red you had basically what was the frame, what was the prediction going on over there. So here you can see that there is a wrong prediction, because the ground truth says that there is no activity, whereas in the prediction it says that the person is pouring water. But then these are all these transition frames. So the person had picked it up and had just put it down over there and has moved out. So this is the phase when you cannot distinctly say whether he is not doing an activity or whether he just finished doing an activity and he is transitioning onto another activity. So there are a bit of challenges over here, but this is not just for a fully connected network. You will have these kind of challenges for your CNN models, for any of your LSTM based models as well, or a CNN plus an RNN combination also. Now finally comes to the point as to where do you think these things are going to get used. Now a lot of this is meant for end products of things which are used in, say for the first case where I showed that there was a surgery being performed and all of this. So these are stuff which are meant for end product use by surgeons or specialists. And if you come to the point that there is an increasing question which gets asked in a lot of community forums is AI going to replace the specialist? Now that is not so. So if you say that is AI going to replace a doctor, no, that will never be able to replace a doctor. And in fact, the AI is never super smart more than the human being. It is the best case smartness of an AI model is limited by the worst case stupidity of humans, and then that's because of the labeling of the data. So you will always need some label data to be given to that, and that will be limited to some point, and your model's performance is also going to be limited. Now the point is that here what you see is an example where there is on the left hand side video which you are seeing. So this big one, this thing is what is called as an ultrasound probe. Now there is a small image like thing coming down at the base of it which keeps on flickering. Now that's augmented reality rendering on top of that. So essentially whatever it's able to see is what is rendered, and what it's able to see is what is given on the right hand side over here. Now on the left hand side what you also do is that what this person is trying to do is that this is a phantom experiment. This is a toy, not a real case, but in the real world this would have been that there is a doctor who is trying to insert a syringe into one of your vessels, blood vessels in your hand or somewhere, which is very deep rooted. So it is so deep that from top it is not able. If I try to look into blood vessels of my hand somewhere very close by or on my wrist, let me see. So here generally it's visible, or otherwise if you just tie that elastic band over there, then blood will start accumulating over there, and then you will be able to see that. Now the point is that in case that the vessel is very deep rooted, then it becomes very hard to see, and so you make use of some kind of a imaging assistance, and here that imaging assistance is using an ultrasound probe. So the point is you are able to see that, but then when this whole needle is going and what angle you are going to insert that, can you have some sort of a predictive control? And that too, like if this is the plane of imaging, but if it is entering from somewhere else, then I don't know exactly where it will cut and enter. So this was all of this where this kind of video tracking actually goes off hell. So as an end product. So here what you can see is that the whole video analytics goes on, and then there are some special markers which we had placed in order to make this one much more easier, because you also needed to calibrate what is the 3D orientation and movement. So X, Y, Z as well as your pitch roll, all of these things needed to be calibrated over there. So that is a bit critical to actually work it out. So now here what we have is that this whole thing, when you are able to do, then the needle of this syringe being in line with the axis over here, and now that is tracked with respect to this, so that can be displayed over here. So this is what is getting displayed in terms of the actual image frame, and what you see over here is that this whole image frame with the actual needle pointer and the trajectory and everything is now aligned with the probe over there. And what that would allow is that for somebody to see, if you are wearing a special kind of a glass called as an augmented reality glass, this can be the, say, a Microsoft HoloLens, or this can be something like a Google Glass, then you will be able to see that image over there. You don't have to turn your head every time in a different monitor and look at it. So ever try working with two different monitors and something in front of you, then you will understand what is that problem which comes down. So these are those end cases which we are essentially looking these kind of solutions which get built up. So this was the final use case, or one of the use cases which I can give you a pointer. So that's where I would come to an end for understanding of temporal deep learning and these things. Now what I would do is on tomorrow's class, which is the next class, I will give you a worksheet so that I will prepare today and give it to you. And so essentially I'm not having tomorrow's class. So this is a worksheet assignment which goes to you to be solved out within the week. And then I'm not going to grade the worksheet. You can grade it yourself. But then please ascertain that you are solving the worksheet itself. Because after that I'm going to come back and send out a quiz to all of you in order to do that quiz. And that quiz will be a graded assignment. But until you do the worksheet, you will find it really hard to do the quiz. And I will come back with the solution to the worksheet after the quiz is done. So that will be the way in which I will evaluate it out. So that worksheet is going to be essentially on what we have covered more or less today, and something associated with and the quiz will also have something associated with the generative models and adversarial learning concepts together. So that's where I come to an end. And before I so Raghavendra, any practical use for tool identification? That's what I said. So essentially, when a surgery is going on, then you need to find out for how many minutes the tool has been used, because this gives you the so life of a tool is limited. Generally, you don't want to lose out the life of a tool. So if some tool is at the end of its usable life, then you don't want to put it into a surgery which might take longer. So it's something like this, that I have only 3 hours of my tool's life remaining. So if there is a surgery which can last anything between 2 hours to 7 hours, I will not risk putting this tool inside over there. If it finishes off in 2 hours, then okay, I can pull my tool out and it's within the safe limit. But otherwise, it's not. Now, if I have a usable life of say 3 hours left on my tool, based on all of these tracking model, all of these classification models that I had, then if I anticipate that there is a new surgery which is coming, which in best case will get over in 30 minutes, and in worst case it's going to take me 2 hours, then I'm going to make use of this tool. So essentially this is for very efficient and optimized utilization of physical resources which you have, as well as for quality control, life monitoring, and all of these things. So is that clear to you? Okay. So, and before I end, there is something which I wanted to show you. So during this time, and this is more of like where you can get some engagement. So this was one of the projects which we launched out recently from our group, and a couple of students from your deep learning class are also helping us do this. There are the TAs for the class are also helping doing this one. Now, what this essentially is, so we are trying to make use of deep learning based methods in order to accelerate how you create standards and data reporting guidelines for radiologists for reporting out COVID-19. So you can actually read through this and then come to the point, and if you are willing to contribute, then there is an option to enroll. So you can go over here and enroll yourself and do it. So what we have been able to do till now is that based on the success which we are showing in rapidly scaling up, we tied up with another challenge on COVID-19 from the European Union, which is a developing of image-based AI solutions for scanning of and diagnosing and grading the COVID-19 severity using CT scans. Then we also released out our RADs, and this is one of the first primary developments which we are doing. So this is the very standardized sort of a checklist for reporting out observations which are seen in radiographs of patients who are suspected to be positive to COVID-19. And this is important when you have the first round of test with the PCR having done, and then you enroll a patient in a hospital for care. In that case, you are giving down treatments and everything, and while the treatment is going on, you need to really assess that whether the patient is responding positively to the treatment or not. And that would mean that you keep on doing continuous evaluations and imaging in order to do that. So if this RADs, or until this guidelines of what to look in an image in order to really say that this patient has this problem or not is of critical importance. So we have put down this initiative to do all of this so as to create the checklist by going through use of NLP tools like strippers and keyword identifiers and spotters in scientific literature. So there were a lot of papers which were coming down in medical literatures. We basically looked through them, and then from there you find out what are keywords and then create a list of keywords, and then you have to reprioritize, deprioritize everything, and then basically create this checklist for doctors to find out whether then there is a hierarchical embedding and everything, which now is a discovery based feature. So there are a lot of engagements in which we are pulling down, and how this is helping is that there is a project which started on 24th or 25th of March itself, just last week. In 1 week, we have the second revision of this checklist which has come up, and use of these kind of AI models has helped us basically scale up from being able to read just a couple of papers a day to look into this and trying to associate, to having done 2 revisions by going through more than 100 of papers and also use all of these developments in order to collect out more annotated image examples and everything. So you basically use images of papers, you have spotters over there, you find out where is a keyword text, where is an image, and then you create something which is called as a case library, and this is for educational purposes for radiologists, that now that there is not much of a time for them to read details through the paper, so can you summarize and generate all of this. So a lot of deep learning tools which we have been developing over the years are coming of use over here, and this is going by the by. So more and more this will increase over the days, and the idea is to create a complete data set which we would release out. So this data set will not just have images, but they will also have annotations in terms of natural language annotations, and then you can use them in order to fill a form, which is that checklist over there. So if any of you guys are interested, then please go onto this website and enroll. So the web and the address is over here, and you can click on this enroll button over here on top of the page, and then that would move you to somewhere over here, and then you can create a stakeholder type. So typically there are multiple stakeholders, and you can think of enrolling as a AI and data scientist, and then so there would be different tasks which come out rolled. So we don't publish out exactly what we are doing over here. They are under a sort of a closed license, which to which you get an email and all the details are told, and then there are some other things which are published directly over here on a Creative Commons license, so that comes up. So that's sort of an information. If you would like to get engaged more with us, then you are also welcome.